Okay. Good afternoon. Welcome back to the weekly live discussion sessions on mechanics and control of robotic manipulators. I am Isaac John. I would be the TA for the course ME92 offered in NPTEL by Dr. Shantakumar Mohan of IIT Palakkad. So, in this session, we'll be discussing uh, a brief summary of lectures that was covered during week 3 of the course. So we'll dedicate the first part of this session to discuss or to have a brief summary of the topics that we have covered over the period of this week. And later, for the later half, we'll discuss a sample questions which you can use it to, or with which you can practice and gain some experience to solve the weekly quizzes as well. So, yeah, once again, welcome to the week 3 sessions on mechanics and control of robotic manipulators. And for the syllabus, we'll be looking in detail the definitions and some examples on forward and inverse kinematics of robotic manipulators. We will see how can we solve inverse kinematics using numerical methods, and why do we have to rely on numerical methods. Uh, we have also discussed the forward kinematic solutions using MATLAB. It has been already demonstrated. It has already been demonstrated in the weekly lectures. And then we have also covered the inverse kinematic solution based on numerical methods using MATLAB. So the purpose is to have a brief summary of all the topics. I won't be showing any simulation for this using MATLAB because it has already been covered during the weekly lectures. But the key idea is to solve weekly. The key idea is to solve some tutorial problems. So I'll be cherry picking some of the relevant topics. Mostly theory. The theoretical background regarding week 3. And like once we have covered the summary of all the topics that we have covered in week 3, we'll solve some of the few questions. Okay, so moving on to the topics. So we have already seen the definitions of forward kinematics and inverse kinematics during the previous weeks. I think in the previous weeks, starting from week 1 all the way to week 2, I think the previous 2 weeks we have already seen what forward kinematics is and what inverse kinematics is. Nevertheless, since it is one of the most fundamental topics of robotic manipulators, we'll still cover these topics in detail. So what forward kinematics says is that it determines the configuration of the end effector for a given relative configuration of each pair of adjacent links, right? So I would like to take an example of a well-known robot or a well-known manipulator. We call this a 2R robotic manipulator comprising of 2 links and which are interconnected by 2 revolute joints. So this is one revolute joint, right? And the axis of this revolute joint is out of plane. So I'll label this as Z1. That is the rotational axis of that revolute joint. And here there is also one more revolute joint. And again, its axis is parallel to Z1, and similar to Z1, its axis is also out of plane, Z2. And it consists of 2 links, the first being marked as link 1, the second being marked as link 2. And at the tip of the second link, we have the end effector. So in this example, I've considered it to be a gripper. So what forward kinematics is that? Like there are 2 joint variables. So in this example, we can the joints being 2 revolute joints here in Z1 and Z2. So this is where we would give the input to the manipulator. For example, this is where we would attach the motors. So I'll label it as motor 1, and here I will label it as motor 2. So depending on the inputs that you give to these motors, what would be the position of your end effector, right? Like for example, if I give this motor input theta 1 to be 45 degrees and motor 2 theta 2 as maybe 45 degrees, what would be the position X and Y coordinates of this end effector. So analyzing that, forward from the joint coordinates or the task space variables uh, to obtain the configuration of the robot is what we call as the forward kinematics, right? So just to give an overview of what these task space variables are, I will give just to recall what are these variables. So joint space variables. So these are, for example, theta 1, theta 2 that can fully describe or fully define the configuration of a robotic manipulator. So like, for example, if you consider this to be theta 1, the angle link 1 makes with theta 1, and theta 2 is basically the relative orientation between theta 1 and relative orientation between link 1 and link 2, right? So these are the joint space variables, the number of inputs required to fully describe the entire configuration of this manipulator, right? And the task space variables would be the X and Y coordinates of the end effector, right? This is what, as from an operator's point of view, the task space variables are, would be the would be the point of interest, because we would desire, or an operator would desire to control a robot with respect to X and Y coordinates, right? That would be much more intuitive for an operator. Like suppose if you want the robot to move anywhere within this entire workspace, we would define this entire workspace in terms of X and Y coordinates, right? Because that is more intuitive to visualize. So the mapping from joint space to task space, we would do this using forward kinematics, right? So in another ways, this is similar to simulating a robotic manipulator. Simulation in the sense, like if you give some particular inputs to theta 1 and theta 2, what would be the final position, or what would be the final coordinates of the end effector, right? It'll be like a virtual simulation of the robotic manipulator, like just to get the feel of this robotic manipulator. Like if you give specific inputs to its motors, where would it be, right? So that is akin to simulating the robot. And if you do this the inverse or the opposite way, from task space to joint space, that is called the inverse kinematics problem. Inverse kinematics. Sorry. So in real world applications, if you want to deploy a robot on a specific application, suppose you want to pick some object from a point of the workspace. Suppose if you call specific point in workspace as x1, y1, if you want the robot to go to x1, y1, and it has to take, or it has to grasp an object, and it has to drop that object on another point of the workspace, x2, y2, then what should be the corresponding inputs that you should be giving onto the motors of this robot? So inverse kinematics deals with these sort of problems. It's akin to controlling the robotic manipulator, right? So if the robot has to be at x1, y1, instead of this arbitrary configuration, the robot will be in this configuration. So what should be the theta 1 and theta 2, right? So identifying the joint space variables from the task space variables, so that specific problem is called inverse kinematics, right? For example, if you want to pick up an object from x1, y1, and if you want to drop that object on x2, y2, then what should be the task space variables theta 1 and theta 2? So this would be the problem of inverse kinematics, right? So in a way, forward kinematics is similar to simulating the robot, and inverse kinematics would be more or less similar to controlling the robot. Controlling the robot. Okay, so moving on, what can we say more about the forward kinematics of a robotic manipulator? Right. So basically, it is the transformation of the kinematic information from robot join variable space to the Cartesian coordinate frame of the final frame. So this is what we have covered previously. So to transfer the information from the join space to the task space using a mapping, so that specific mapping is what we call as forward kinematics. Right. So in this particular example, the join variables would be theta1 and theta2. So for any given join variables theta1 and theta2, what would be the coordinates of the end effector, x and y, right? So this mapping from the robot's base. So if you consider this to be the first link, the base of the robot would be here actually. So propagating the information from the joint, from the base, all the way to the end effector or the gripper in the specific example is what we call the forward kinematics of a manipulator. The traditional way of producing the forward kinematics equations for a robotic manipulator is to proceed link by link using the DH notations and frames, right? So in the previous week, we have seen how to do this DH mapping or how to attach or how to uh, fix the frame as per the DH convention and how to derive the transformation matrix from with the help of this DH parameters. So like I'm not going to derive it, but just to give a brief overview of the procedure, we would first attach the frames for this specific manipulator. So the first frame would be along the axis of the first joint, Z1, and the second joint would be along the axis of Z2, right? So I'll label here it as the first frame. This would be the second frame. And we would have two more other frames. The third frame would be the at the tip of this end effector. This could be frame 3. And there is also one more frame. We call it as frame 0 that would be attached to the base. So the forward kinematics is basically nothing but the propagation of the transformation matrix all the way from 0th frame, 0t1 multiplied by 1t2 multiplied by 2t3 multiplied by, yeah, I think that's about it, 0t4, right? And these are all 4 by 4 homogeneous transformation matrix. And you can use the DH parameters to populate each of these individual matrices. Now you can use the DH parameters for between join 0 and join 1. You can use the DH parameters between join 1 and join 2 to obtain this transformation. And similarly, the DH parameters between joins 2 and 3 to obtain this transformation matrix. And if you multiply this like this sequentially, you will get the information, you will get the mapping from the 0th frame all the way to the final end effector frame. This should be 3. Yes. So that is how you derive the forward kinematics equation for the robotic manipulator, for any robotic manipulator. And what is the third point? Hence, the forward kinematics is basically the transformation matrix multiplication, right? So if you multiply it throughout like this, all the way from the 0th frame to the 3rd frame, you will get the forward kinematics equation of a specific robotic manipulator. Okay, so another thing that we have covered during the lectures is to assign or to define what these vectors are, that is, that is mounted at the end effector. Like for instance, if I go back, we say that we have one more frame at the tip of this end effector over here, right? Like apart from the joints, we have one more frame attached at the tip of this end effector. This is necessary so that we can get the final coordinates of this end effector. And there is a specific convention regarding how we name this each and every axis of the end effector, right? So one of them is called the normal vector, the second one is called an approach vector, and the third one is called the sliding vector. And you can consider this to be the plane of an end effector, right? It could be considered as a gripper where you can have a tool like this, and the gripper would essentially exert some forces so that it can hold on to this tool or any object of interest. So we'll define one by one each of these each of these axes. So the first one is actually called an approach vector that is aligned with the tool axis, right? The first one is actually called an approach vector. So if I consider this to be a tool, uh, please excuse my very crude drawing. So if you consider this to be the tool tip, so the axis that is aligned along the longitudinal axis of the tool, you name this as approach vector, right? It specifies the tool point direction. So that is the first vector. The second vector, we call it as the sliding vector, which is orthogonal to the approach vector, right? So orthogonal to approach vector means it can be 90 degrees. So it can be along this direction, it can be along this direction. So it can be along 90 degrees, any of these directions with respect to this approach vector. But we need one more information to exactly specify that location, right? So what would that be? So that says it's orthogonal to the approach vector and aligned with open and close axis of the tool, right? So if you consider this to be the gripper, and the gripper can open and close along this direction so that it can exert some gripping force onto the tool. So like maybe using some sliding joint, that gripper can move back and forth along this direction. So that specific direction, which is orthogonal to this approach vector, we call this as sliding vector, right? Sliding vector. And the remaining vector would be perpendicular to either of these vector, sliding vector and approach vector, that is called the normal vector, right? It's just normal vector is simply orthogonal to the plane defined by the approach and sliding vectors. So it completes the right-handed orthogonal coordinate frame, right? So how do you define these vectors? So typically, as per the convention, like we know the rotation matrix is a 3x3 matrix, right? It's an orthonormal matrix. So the first column would consist of the normal vector, nx, ny, nz. So this would be the first column of the rotation matrix. And the second column would be the sliding vector, sx, sy, sz. And the third column would be the approach vector, which would be ax, ay, az. And like from the properties of the rotation matrix, it should be clear that the rotation matrix is orthonormal. So which means R transpose R or RR transpose is an identity matrix, right? And the magnitude of each of these vectors is 1. So like if you take the magnitude of this column, it should be 1. The magnitude of this column should also be 1. The magnitude of this column should also be 1. So that is just about the convention that we would use for naming the axes on the end effector. Okay, so now we move on to the inverse kinematics. So again, just like what I have mentioned, it's a problem of determining the joint variables of the robot for a given configuration of the robot. Like just like an example, just like what we have considered earlier for a 2R robotic manipulator, right? So let this be a general configuration of a 2R robot, assembled using revolute joints. So like just as I've said earlier, if you have a position x1, y1, if you want the robot to move to this position x1, y1, what should be the joint coordinates θ1 and θ2, right? Because that is what you want to input into the motors to realize this position, right? So to determine the corresponding joint variables x1 and y1, the problem of determining the joint space variables for the corresponding task space variables is what we call the inverse kinematics problem. So determination of the joint variables in terms of the task space, position, and orientation is called inverse kinematics. So in this specific case, we are only considering the position. There is no orientation in this specific problem. right? Because in the case of a 2R manipulator, it only has 2 degrees of freedom, and it can only control, or it can only realize positions in a 2D space. It cannot reach any arbitrary orientation with respect to the 2D space. So in this specific example that we are considering, we are only dealing with position, not the orientation. But in any general case, the determination of the joint variables in terms of end effector position and orientation is called the inverse kinematics. The third point is, although there are no standard and generally applicable methods to solve inverse kinematics problem, there are a few analytic and numeric methods to solve the problem. See, the problem with the inverse kinematics of serial robots is that sometimes the equations are too complex to solve analytically. Like for example, in this case, this is a 2 degrees of freedom robotic manipulator. So if the degree of freedom is very low, or if it is less than 3, in such cases, uh, deriving this inverse kinematics problems is much simple. You can derive it using analytical methods. But if the number of degrees of freedom goes beyond 3 or 4, maybe for example, in the case of a 6 degrees of freedom robotic manipulator having 3 positions and 3 orientations, deriving this inverse kinematics equations would be very difficult. So in that case, you have to resort to numerical methods, right? Numerical iterative methods to obtain the inverse kinematic solutions. Okay, and the main difficulty of inverse kinematics problem is the existence of multiple solutions. So like, for example, in this case itself, you can have multiple solutions, right? I'll demonstrate this with one example. So if this is the target point that you want to reach, x1 and y1, and if this is the base of the robotic manipulator, it can reach the end position by 2 approaches. The one would be like this. This would be one position, right? It can also achieve this position using another configuration, right? This is the second solution. So the first solution is like this. The second solution is like this, right? So a manipulator having only 2 degrees of freedom has 2 solutions. And in the case of a manipulator having more than 2 degrees of freedom, maybe 4 or 5 or 6 degrees of freedom, it can have multiple inverse kinematic solution for a specific pose, or for a specific position and orientation of the for the robot. So it would be very difficult to track all these solutions simultaneously. So yeah, we typically encounter these difficulties in inverse kinematics problem. Okay, so more on inverse kinematics. This is just as a summary to what we have discussed during the lectures. So computer controlled robots are usually actuated using joint variable space. Like for example, if you want to control a robot like this with 2 revolute joints, the inputs to be given to this robot are at the joints, are through these joints, because this is where the motors are mounted. Motor 1 and motor 2. So at the joints, we would have the motors mounted. The second point says, however, the objects to be manipulated usually are usually expressed in Cartesian coordinates frames. For example, if you want this robot to pick an object from x1, y1 and to place it on x2, y2, we define the initial position of the object using the Cartesian coordinates x and y, and the dropping position of the object using x and y. So like there is actually a conflict, because controlling is happening in joint space variables, right? And objects are expressed in Cartesian coordinate frame. So due to this, therefore, carrying the kinematic information back and forth between joint space and Cartesian space is needed in robotics. So due to this conflict, controlling the robot in joint space and manipulating the object in Cartesian space, we would have to go back and forth between joint space and Cartesian space. And to control the configuration of the end effector to reach an object, the inverse kinematics problem must be solved. Right? Like if you want to command the robot to go to a specific position, you would need to know what should be the inputs that you need to give to this motors. So that is why we require this inverse kinematics. Okay, so the typical features of inverse kinematics is that it is more difficult in case of a serial robot to solve, right? And the equations to solve are non-linear. So thus the closed form solution is not always available, right? For higher degrees of freedom robots, the closed form solution is not easily derivable. And the solution is also not unique, right? Just like what I have shown you earlier, the solution, it can have multiple solutions, right? So like there could be robots that has more number of joints than the degree of freedom that we would be controlling. So the solution may not be unique. We have to track multiple solutions simultaneously. And the complexity of this inverse kinematic solution could be dependent on the robot. So this is unlike the forward kinematics because it is very easy to derive. Like if you follow that DH convention in assigning the frames, and if you systematically derive that DH parameter table, you can easily derive the forward kinematics equation. But in case of inverse kinematics, it depends on the robot, right? Like for smaller robots, it could be easier to solve. And for robots which have higher degrees of freedom, it could be very difficult. And sometimes it may not be even possible to derive a closed form solution, right? So in such cases, you will have to resort to numerical methods. Okay, so there are two ways of solving the inverse kinematic solution. So the one approach is numerical methods, which that is what I've just said. And the second approach is the closed form solution, right? And the main differences between the numerical and the closed form solutions are summarized here. So in numerical solutions, the results are numerical. They follow some iterative procedure. Like for example, we know how to solve nonlinear equations using this Newton-Raphson techniques. There are other techniques called this regular falsy methods. You can also use bisection methods. All these possible methods are available for solving numerical methods. Whereas in the case of closed form solutions, analytical solutions to a system of equations, we have to derive from the analytical solutions so that the final closed form solutions can be obtained. So we don't know the number of solutions number of operations that is required to solve the numerical method, because all these things happen in the background. It's like a black box, because we don't know how many number of operations that is required to solve an inverse kinematic problem when it is run in the background using a black box. So the problem with this is that if we don't know the number of operations, we also will not be able to say how much time it'll take to solve an inverse kinematics problem. Right? If we know the number of operations, like we can at least have an estimate regarding how much time it would take to solve a problem. But that is not the case for closed form solution, because it can be solved by a fixed number of operations, because we already have the equations on our hand. And because of that, we can estimate how many number of operations like additions, multiplications, subtractions. So the computational time is known. We can actually estimate the computational time for closed form solutions. And in the case of numerical solution, it will only return a single solution. It will only return a single solution. So this is a problem with typical numerical solvers, because it will only converge to it will only converge to a minimum. It will only converge to a local minimum. it may not even converge to a global minimum. It'll only converge to a local minimum. And in most of the cases, we have to ensure that that local minimum is also the solution that we are expecting. And which solution this would be converging, it will depend on the initial guess or the initial conditions that we are giving, right? Like for example, in the case of a 2-hour robot like this, right? We have said that it can have two solutions. One solution is like this. The other solutions could be like this, right? And in the case of a numerical solver, it can only converge to a single solution. And again, that also depends on the initial condition that we are giving. But in the case of a closed form solution, we can actually estimate all the possible solutions because we already have that final closed form solution in hand. And the accuracy is actually dictated by the user, right? So like if you are running some iterative methods, we have to terminate this iterative method. And usually the way with which we would be terminating this iterative method would be based on maybe a tolerance, right? If two successive iterations are very small, we would then terminate this iterative method. So the accuracy of this numerical solvers are mostly dictated by the user, whereas that is not the case for analytical methods. And due to this, it is not really desirable. It's much less desirable in case of uh, a real-time control, actually, because the big reason is that we don't know the computational time. And since the accuracy is already dictated by the user, deploying this approach in real-time usage is much less desirable than the closed form solutions. And one specific advantage is that numerical solutions can be applied to all robots. Like irrespective of the configuration of the robot, whether it is 2D off or whether it is 6D off, we can apply this numerical procedure to any of all of such robots. Whereas in the case of a closed form robot, it cannot be applied. It can only be applied for robots which have simple kinematics or simple topology. So that is the main difference between numerical solutions and closed form solutions. Okay, there is actually one more problem. We may face some interruptions in between during the session. So we may face an interruption within 8 minutes. So I will restart the session. So please feel free to join back if you finally face yourself suddenly cut out from the session, right? So the duration of the session is 2 hours. It will go all the way to 5 p.m. So hopefully by 4 o'clock we will solve some sample problems. But if you find yourself being cut off from or being expelled from this session, please feel free to join back. Okay, so there are also a few more points that I would like to discuss. The conditions for existence of a closed form solution of a 6-axis robot, right? A 6-axis robot have 6 active joints, right? So such robots can have all 3 positional capabilities, and at any specific position, it can achieve any possible orientations. So it will have 6 degrees of freedom, 3 positions, and 3 orientations. And most often, you cannot solve the kinematics of a 6-axis robot because the equations are far too complex. Okay, so I have actually got a question. How much is the convergence time in numerical analysis? So we cannot have a definitive answer for this because it depends on the robot. It depends on the complexity of the robot. For example, in some cases, solving a 2D of robot will take lesser time than solving a 6D of robot. And it also depends on the tolerances that you would give onto the solver. Maybe if you If the step size is smaller, it will take more time. If the number of function evaluations is also higher, it will again take more time. So like it depends, it depends on the solver settings. It depends on the complexity of the robot. So like generally, like for simple robots, it takes less time, but for robots with more number of equations to be solved, it takes, more time. But we cannot have a definitive answer like like that.
Actually, in the table, we have the points, na, sir. So that's why I
Yeah.
asked. First category is the numerical, and the second one is the
Yes.
closed form, na, sir. In
Yeah.
that
Yeah.
point, I am asking.
Okay. So the key thing is numerical solutions would usually take more time. More time to
Oh,
solve than
okay, sir.
closed form solution. Because like in closed form solution, we already have this equation and we only need to substitute some numerical values into this equation. We'll readily get this answer. But in case of a
Okay,
numerical solution, every time it will have to solve this. It will have
okay,
to
sir.
solve this equation numerically, right? So
Thank you,
as a
sir.
thumb rule, yeah, numerical solutions will take more time than closed form solutions. Okay, so continuing with the case of a 6D of robotic manipulator, as I've mentioned in general case, it'll be very difficult to solve the inverse kinematics of a 6 degrees of freedom robot. But there are cases where you can solve, there are specific exceptions where you can solve the inverse kinematics of the robot using, pen and paper. You can simply derive the solutions using your hand. And those specific cases are listed below. So one of the cases are, so in the case of a 6 degrees of freedom robot, if the three adjacent revolute joints axes intersect at a point, that is one such cases. And the second condition is if the three adjacent revolute joints are parallel to one another. So like in any case, algebraic or geometric intuition is to obtain the closed form solution. Like I'll show one example. Like if we have a robotic manipulator that has three, parallel revolute joints, I'll label this as Z1, Z2, and Z3. So these three revolute joints can control the position. And if we have three more revolute joints, but this time it will be intersecting actually. So this will be, so Z4 will be, oh no, sorry, Z4 will be like this. Yeah, this is Z4. Z5 would be like this. And Z6 would be something like this. This is Z5, this is Z6. So in this example, the final three joints are intersecting, right? So essentially, we can decouple this inverse kinematics problem using inverse position kinematics and inverse orientation kinematics. So typically, if any of these two successive conditions are satisfied, you can solve the total inverse kinematics problem using these two approaches, right? You can split the inverse kinematics into inverse position kinematics and inverse orientation kinematics. So the basic principle is that, so if you try to solve the inverse kinematics of this entire manipulator, it will have 6 variables, right? It will have theta1, theta2, theta3, theta4, theta5, theta6. So like there could be many equations having all these variables simultaneously. And solving simultaneous equations with these many variables, it will be sine theta1, cos theta2. So that'll be very difficult to solve such a problem. So the easiest way is to decompose the inverse position in total inverse kinematics into inverse position and inverse orientation. So the procedure is that like if you the position of this end effector or the final gripper will be given. So if that is given, you can solve the inverse position kinematics, and that will only contain the first three variables, theta 1, theta 2, and theta 3. Right? If the final tip end effector pose is known, because that is what the inverse kinematics. It will first give you the pose, then you have to find out the joint variables. So if the position is known, then you can actually find out theta 1, theta 2, theta 3. You can first solve the position problems because it will only contain equations having the first three unknowns, right? Theta 1, theta 2, theta 3. So from inverse position or inverse position kinematics, you can get theta 1, theta 2, theta 3. So once you have solved inverse position kinematics, you can you can substitute these numerical values into the inverse orientation problem, and then later you can solve theta 4, theta 5, and theta 6. Right? It's basically decomposing these entire problems into two problems. The first is inverse position kinematics, and the later being inverse orientation kinematics. So this can only be possible, decomposing this into inverse position and inverse orientation. It's only possible when you have either of these two conditions. When three adjacent revolute axes intersect at a point, like in this example, right? Because the final three points intersect at a point, right? Yeah, so if either of these two conditions are satisfied, you can decompose the inverse kinematics into inverse position kinematics or inverse orientation kinematics. So with inverse position, you can solve the first two variables, theta 1, theta 2, theta 3, and using inverse orientation, you can solve theta 4, theta 5, and theta 6. Okay, so moving on, I would like to demonstrate an example using the solving this inverse kinematics of an RP robot. So typically, what you would first do is to first assign the frames on using this modified DH parameter convention, right? But in the case of a manipulator that is as simple as this only has a 2D of 2 degrees of freedom. You can derive the final equations without the need of the DH parameters, right? So speaking more about this robot, this is an RP robot. This R stands for the revolute joints, revolute, and the P stands for the prismatic joints, right? So yeah, it consists of two links. So this is the first link, the outer outline, like what I'm highlighting here, like this. The first link. So it can rotate about this global z-axis. So this is the global y-axis, ya, and this is the global x-axis, xa. And the global z-axis is out of plane like this, right? So this link one can rotate about this global z-axis, and it is characterized by this angle, the joint variable theta 1. So this this link can rotate, about this z-axis. And we also have a second link like this. Okay, hold on one second. I may have some issues because the participants have still not joined. So let me check if I need to do something from my end. If it is, let me stop sharing my screen. Stop sharing my screen. Okay, so people are able to join, right? So yeah, in that case, then I can continue. Okay. Okay, so just as I was mentioning, we have two links. The first link is what I'm highlighting over here right now. So it has, hold on one second. Yeah, it has a degree of freedom about the global z-axis that is out of plane, right? So it can rotate about this global z-axis, which is characterized by this joint variable theta1. And the second link is what I'm highlighting over here like this. So the relative position between link 2 and link 1 is defined by this joint variable d2, right? Because it's a prismatic joint. So link 1 can rotate about z-axis, and link 2, this being the link 2, it can slide, translate back and forth about link 1 like this. So if I call, or if I define the final point and effector point as x and y, how would you write this coordinates x and y using the joint space variables? So one way to use is to follow the DS approach. You know, if you assign a frame 0 on the ground, and frame 1 on link 1, and frame 2 on link 2, and maybe one more frame if it is needed on end effector. So you can derive it using the DH method by following the successive transformations from 0t1 to 1t2 to 2t3. That is one approach. But I'm more comfortable to write this directly, because this is a 2D of robot, and in case of a 2D of robot, you can directly write this equation without relying on the DH parameters. So the x position would be it'll be d2 cos theta1, right? If I highlight this, if I highlight this as x, and if I highlight this as y-axis, and the y coordinate would be d2 sine theta1, right? Where theta1 and theta2 are the joint variables, right? So for a given x and y, how would you solve the joint variables d2 and theta1? d2 and theta1. d2 is a prismatic joint variable, and theta1 is a revolute joint variable, right? So inverse kinematics is solving these two kinematic equations, equations 1 and equations 2. How do we do that? So if I simply square and add the first two equations, equation 1 square plus equation 2 square, this would yield x square plus y square as t2 square cos square theta1 plus t2 square sine square theta1, right? So simplifying this, you will get d2 as x square plus y square under root. So you have solved for one of the joint variables. And what about the other joint variables? So if I divide equation 2 by equation 1, so d2 sine theta1 by d2 cos theta1, this would be y by x, right? So tan theta1 would be y by x, or theta1 would be tan inverse y by x, right? So with this, you have solved for the joint variables d2 and theta1, right? For a given x and y Cartesian coordinates. That is one way of solving the inverse kinematics, right? Okay, so What about one more example? So we have talked so far uh, about this RR robot, but how do we solve this inverse kinematics of this RR robot? So this is the y-axis, this is the x-axis. So I'll label the 2R manipulator like this, or maybe I'll draw a better picture. Yeah. So instead of using this thick lines, I'll use thin lines. I hope that should be fine. Right. So this is the first joint. This is the second joint. And I'll label these as link 1. This is link 2. And the coordinates of this tooltip would be x and y. Right. And the joint variables would be characterized using this joint variables theta1. That is the uh, orientation between link 1 and the x-axis. And we have one more joint variables that depicts the relative orientation between link 2 and link 1. This is theta 2. So for a given x and y coordinates, how would you determine theta 2 and theta 1? Right. So the procedure is like this. Just extend this a bit more further. This is x-axis. Right. So what I'm doing is I'm simply projecting this coordinates on x and y axes. Y. Yeah, I'm simply projecting this. So this distance would be x, and this distance would be y, right? And if I draw a vector like this, maybe a vector like this, right? So what is the length of this vector? I'll label this vector as r, right? So what is the length of this vector? This vector is nothing but, like, if you consider this to be a right angle triangle like this, right? So r square would be x square plus y square, right? So I'll write it over here. R square is x square plus y square. I'll label this as equation 1. And if you again consider this triangle, it's not a right angle triangle, right? If you consider this triangle, and if you consider the link lengths to be L1 and L2, right? L1 is the length of this link and L2 is the length of this link. And again, if I simply, for the sake of convenience, I will define this angle as alpha. So what is R using this law of cosines? So R square would be, I'll just try to use the same ink. So from law of cosines, R square is nothing but L1 square plus L2 square minus 2 L1 L2 cos alpha. I label this as equation 2, right? So L1 square plus L2 square plus 2 L1 L2, this is this angle, sorry, this angle, right? This angle is alpha. So from comparing 1 and 2, you can write it as x square plus y square is L1 square plus L2 square minus 2 L1 L2 cos alpha. And I would like to bring cos alpha to one side and everything else to the other side. So how would it look like? X square plus y square minus L1 square minus L2 square by 2 L1 L2. This would be minus cos alpha. I hope you would agree with this, right? Now that we have solved this cos alpha, how can you relate this alpha to this joint variable theta 2? How would that be possible? So alpha and theta 2 are related by this relation. Yeah, one alpha plus theta 2 is 180 degrees, right? So so in that case, theta 2 would be 180 minus alpha. Or in another way, yeah, alpha plus theta 2 is 180 degrees. So alpha is 180 minus theta 2. So if I take cosine of on both sides, cos alpha would be cos 180 minus theta 2, right? So if I expand this, this will be cos 180 cos theta 2 minus, sorry, it will be plus sine 180 sine theta 2, right? So what is cos 180? So this is cos 90, 180 is minus 1, right? So cos alpha would be minus cos theta 2 and sine 180 is 0, right? So cos alpha is cos minus theta 2. So in this case, minus cos alpha, in this equation, minus cos alpha would be minus of minus cos theta 2. That will be simply cos theta 2, right? So if I replace this with positive cos theta 2, right? So you can solve for theta 2 like this, right? So you have solved for theta 2, right? Because, yeah, theta 2 now would be r cos.
Sir, excuse me, sir. Sine theta to what happened, sir? In the
Sine theta 2
derivation?
would be simply 1 minus plus or minus root of 1 minus cos theta 2, right?
Okay.
Square, right? So the thing
Okay.
is, you can have two solutions for this, right? So like, for example, you can have two solutions. So one solution would be like this, and the other solution would be like this. That you can obtain from that sine theta 2 would be 1 minus cos theta 2, the whole square under root. This will be plus or minus. So that is one way of looking at it. So now that you have solved for this theta 2, you are left with one more joint variable, that is theta 1. So how do you solve theta 1? So in this case, if I label this entire angle, from 0 all the way to this line R, if I label it as theta t, and if I label this angle as beta, right? I hope that is clear. This angle is theta t, and this angle is beta, right? And I am also drawing a perpendicular from this xy like this. This is now 90 degrees. If I'll use a different ink, maybe like this. So now this is a 90-degree triangle, right? This one. So yeah, I'll write this tan beta. So tan beta would be, what would be tan beta? Tan beta would be this opposite side by this adjacent side, right? Opposite side would be this. That would be nothing but L2 sine theta 2, right? L2 sine theta 2, and adjacent side would be this one. That would be L1. This side would be L1, and this side would be L2 cos theta 2. L2 cos theta 2, right? And now one more thing. What would be this theta t? So tan theta t, this would be, so if I consider this to be a right angle triangle, right? So tan theta t would be opposite side by adjacent side. So this is opposite side. That is nothing but the y coordinate, and adjacent side would be nothing but the x coordinate. So tan theta t would be y by x. So beta would be arc tan L2 sine theta 2 by, sorry, there is also an L1, right? Adjacent side would be this length plus this length. This length is L1, this length is L2 cos theta 2. So that makes it L1 plus L2 cos theta 2. And theta t is arc tan y by x. So that makes it, so theta 1 would be theta t minus beta. So theta 1 would be theta t minus beta. So yeah, this is how you would solve the inverse kinematics of an RR robot. So this is only a single solution. There is also one more solution like this. So I have only drawn a single solution, this one. And using similar approach, you can also solve the other solution, which would be something like this. Right? The methodology is just simple, but the angles changes relatively. Right? This is one solution. Other solution, I am not deriving it, but the procedure is more or less the same. And this is the second joint. Yeah. So like as I've already said, you can only use this methodology, or you can only solve the inverse kinematics for a few robots. So one example is this RR robot. The other example was this RP robot. And we can also solve this inverse kinematics for 6-axis robot, provided it follows these two conditions that we have seen earlier. But it may inverse kinematics may not be available for all robotic joints, and because of that, we have to resort to numerical approaches. So just to give a brief summary of the procedure of the numerical approach, uh, yeah, because it's very important, because for a lot of manipulators, the analytical solution, just like what we have seen, may not be available. So the brief summary is as follows, which is for the numerical or the iterative solutions for inverse kinematics problem using Newton-Raphson methods. So the objective is we would be given a mu or a desired task space variables, right? So I'll denote the task space variables here as mu, task space variables using the vector mu, and joint space variables using the vector q, right? So we also know a mapping between mu and q, right? So if you are given a q, how would you find mu? That is using this mapping. We also call this as forward kinematics, right? So mu actual would be given as a mapping of q actual. So we can actually decompose this q actual as q guess plus some delta q. Because q guess is something that we would be giving as our initial guess, and we have to progressively improve our q guess such that at the end this q guess plus this delta q would converge to mu actual, right? So if I do a Taylor series expansion for this function, so mu actual, I carry over this to this right to here, and the Taylor series expansion for this function would be f of q guess plus dou f by dou q into delta q plus the higher order terms, dou square f by dou q square delta q square, higher order terms. So if you consider the step size to be very negligible, you can consider this higher order terms to be very negligible, right? So you can also substitute in place of this. You can also call this as mu actual. I carry over this like this. So function of q guess, f of q guess would be mu guess, right? So the forward kinematic mapping of q guess would be mu guess plus you can label or you can call this term as delta mu. This entire term dou f dou q guess by dou q guess as delta mu. So if we compare these two expressions, what would be this delta mu? So delta mu would be this term, dou f by dou q by dou q into delta q. And you can label this entire term as J of Q. It'll be a Jacobian matrix of Q with F with respect to Q, right? So depending on the robot, you may have multiple F. So F can be a vector, F1, F2, F3, etc. And Q can also be a vector of Q1, Q2, Q3, etc. So this J of Q would be, you have to make a Jacobian matrix out of this. Dou F1 by dou Q1, dou F1 by dou Q2, dou F1 by dou Q3. example, like so forth. Dou F3 by dou Q1, dou F3 by dou Q2, dou F3 by dou Q3. So this is how you construct this Jacobian matrix. So this delta mu would be this Jacobian matrix multiplied by delta Q. So now this delta Q would be J inverse Q guess multiplied by delta mu, right? So your Q, if you convert it into an iterative algorithm, you can call this Q delta Q as the difference between Qi plus 1 and Qi, right? The current step and the next step. So if you do that, the next, the algorithmic representation would be Qi plus 1 would be Qi or Q guess plus J inverse Q guess multiplied by delta mu. Because all these things are available, this is what we need to find out. And iteratively, we keep on updating this Qi plus 1. And finally, we have to terminate if successive iteration between Qi plus 1 and Qi, if I call this as Qi, if the difference between these two becomes very small, maybe 10 raised to 5 or something like that, then you can terminate this iteration. So you have to keep on iteratively performing this step until the step size or the function evaluation will not give you any large difference. It will become more or less similar, right? All these things are given. So at the initial step, Q guess, we assume a Q guess, and the Jacobian we can derive the Jacobian of a robot, depending on its architecture. And del mu would be the difference between our actual desired position and our current position in joint coordinates, right? So del mu would be mu actual minus mu guess. And this mu guess would be nothing but the function or function of q guess. And all these parameters we have at our hand. Our objective is to iteratively find qi plus 1 until the tolerance comes to a very small value. Okay, so that is a brief summary of the numerical method to solve inverse kinematics. And if you if you can recall, there is an example that is being solved in MATLAB, as well as using using the pen and paper approach in one of the professor's lectures. Okay, so with that, we will go to a few sample tutorial questions for week 3. Please let me know if you have any doubts while we are solving the questions. Okay, so question 1 says, which of the configurations will give a spherical shaped workspace, right? Like, for example, we have so far seen a few different kinds of robot. One of the robot was this RR robot like this. And the workspace of an RR robot would be like, a donut, where the radius of this outer circle would be L1 plus L2, and the radius of the inner circle would be L1 minus L2. And we have also seen an RP robot like this. It will rotate like this. One link would rotate like this. Another link would be a prismatic joint that can move back and forth. So in this case also, it can reach any point in this XY space. It can be like a square, like this. No, it can also be a circle like this. Right? It'll also be a circle like this. So the maximum radius of the circle would be the maximum length at which the piston is extending. And the minimum length of the circle would be the minimum length at which the piston is contracting. And there could be another cases also, like in case of a 3D robot, there could be workspace just like a cube, like so. There could be a workspace like a cylinder in case of a specific configuration like so. But in the question, it typically asks you to specify a configuration which will yield a spherical workspace, right? So the easiest way is to identify how many coordinates you require to define a spherical workspace, right? Because we already know that in case of a spherical workspace, for example, if I draw something in spherical coordinates, maybe something like this. This is X, this is Y, and this is Z. So if I have a vector that is projecting out like this, we will use a different line, right? And so if this vector is rising above the XY plane by an angle of theta, it could be a bit hard to visualize this, right? So the angle could be vertically rising, by theta, and yeah, what else can we say? And it is also inclined with respect to this X and Y axis by maybe an angle phi, like this. right? And if I denote the length of this vector as r, what would be the x and y coordinates? So the x coordinate is that first you have to bring this vector to this xy plane, right? To do so, you have to project this vector on this xy plane. So that will be r cos theta, x would be r cos theta. Then once you project this vector onto this xy plane, it will be lying along this line. And further, you have to project this line along x-axis. So again, you have to take one more cos component, that would be cos phi. And the y component would be project this vector along the xy plane like this. So again, we'll have this r cos theta. And now you project this vector onto the y-axis like this. So that becomes sine phi. And z-axis would simply be r sine theta, right? Irrespective of z component will only depend on the elevation, actually, theta. So if you simply rotate it about x-axis, it still would remaining be the same z. The thing is, if you simply multiply square and multiply everything, x square plus y square plus z square, this would give you r square, right? If you multiply all these three equations, you will get this r square. So if you can take a look at this, how many coordinates you require to fully describe our space in spherical coordinates? You require three variables. One is theta, another is phi, and the third is r, the radial distance, right? And to have a workspace, to have a spherical workspace like this, how would you arrange your links? And these conventions denote, the first two joints are parallel, and this rotates. This denotes the axis of this and this revolute joint and this prismatic joint to be perpendicular. So this means perpendicular. This means parallel. So to get a spherical workspace, what should be the coordinates? So if you can take a look at this, here rotation is about one axis, the rotation is about a perpendicular axis. So you would need two orthogonal revolute joint. So if this is one revolute joint about this axis, maybe I'll label this as Z1, and the link will rotate about the vertical x-axis. And the second axis would be something like this. And this would be out of plane. I'll label this as Z2. And finally, we have one more link like this, which would be something like this, which would be a prismatic joint, which can extend or contract like this. Okay. This is a prismatic joint. Prismatic joint, and these two are revolute joints. About Z2 and Z1, we have revolute joints. Right? So I hope you can visualize this. If you have a robot that rotates about this vertical axis, Z1 and Z2, and it can also transverse or translate along this axis, the workspace would be a spherical workspace, right? It will be a spherical workspace. It can, like if you disable this Z1 axis, if you only consider Z2 and this P, it'll describe a circle like this in a plane. And if you rotate this circle over a plane with respect to this Z1 axis, now you enable it, it becomes a sphere, right? So the
But how to
configuration,
get theta, sir? How to get theta,
sorry,
theta variations, right?
uh,
How to
you know,
get
one theta would vary about this Z1 axis, that is theta 1, about this axis, the vertical axis. The other would be out of plane. This would be theta 2. right? And the final one would be this translation, maybe D3, right? So like if you do this DH approach, or if you assign frames and you know if you assign this frames, and if you write the forward kinematics equation, finally you will get up these equations, r cos, like instead of theta 1 and theta 2, I have used it as theta and phi, but in the end you will get an equation similar to these equations, right? So what is the configuration of this? So we have two revolute joints and one prismatic joint. So the first two revolute joints, if you can observe, first revolute joint is like this, second revolute joint is like this, and these two are obviously perpendicular. So you can write a perpendicular symbol between this. And what can you say about these two revolute joints, R and P? So the second revolute joint is like this, and the prismatic joint is like this. Again, both of them are perpendicular. So again, you will also have a perpendicular side like this. So in that case, the correct answer is R perpendicular P, right? And the correct answer in this case would be, I think, option D here. I hope that is clear, right? The question asks a specific, a spherical workspace, right? So this robot with one revolute joint about the vertical axis and the second be out of plane, and the third prismatic joint like this, it describes a spherical workspace. If you draw a circle in 2D and if you rotate the circle about this vertical axis, you will get a spherical, a spherical workspace. A spherical workspace, I don't know if I can draw this properly like this. Like so.
Sir, can we try now the last one, sir? R perpendicular P, what will happen?
R perpendicular
In the
R.
middle, P is there, no, sir, last one.
Is this the case?
Yes, sir.
This case, huh?
Just we will analyze, sir.
Okay, so if you have a revolute joint, I'll denote the first revolute joint like this. Okay, the thing is, one more time we may have an interruption within 2 minutes. So if the meeting is interrupted, please feel free to join back. We may continue this discussion. So the first revolute joint, if I assume it to be like this, about this axis, this is Z1. And the second joint is a prismatic joint. It's a P joint like this. So we have one link like this. And if you draw a prismatic joint like this, what will you get? Yeah. Let me see if I can draw this. A prismatic joint like this. Sorry. So this is the cylinder, and if you have a piston like this, so I label this as Z2. And yeah, now what will be the workspace actually? It'll just be with these two links, it'll just be a cylinder, right? Or it'll be just like a circle. It's a planar workspace, right? For example, it'll be like the workspace would be like this. For example, if you consider, yeah, you were mentioning about this case where we have a revolute joint and a prismatic joint and another revolute joint, and all of them are perpendicular. So here I have constructed two joints. Until now we have considered these two joints. So the first joint is about this vertical axis, a revolute joint. And the second axis is a prismatic joint that is perpendicular to this R joint. And it will move along this axis, Z2. So just with this, how would the workspace look like? It'll look like concentric circles, right? About concentric circles. And this the circle, the plane of the circle is normal to Z1, right? Like for example, when this prismatic joint is fully extended, you will get the largest circle. And if the prismatic joint is fully contracted, you will get the smallest circle, right? Okay, so it will be a circle for now when you have R perpendicular to P. Now we have one more joint that is again R that is also perpendicular to this R. But how would you attach this R joint? Okay, the workspace depends on how you would attach this R joint. It should be perpendicular to this prismatic joint. So I hope you would be fine if I attach something like this. Maybe Z3. So if you have a revolute joint like this, and one more link like this, what would be the workspace look like? It's not spherical, right? So at each point of this, at each point of this circle, it'll again draw a circle like this. That is what it is going to draw. Like this entire thing can rotate. If it is fully extended, it'll draw a circle like this about this Z1. And at the same time, it will also have this joint will also rotate like this. Right? So that is not a spherical, it is not actually a spherical workspace.
That means always, most of the time, position should be the end at the end. It is better.
Uh,
P.
yeah, P would be mostly at the end actually. There could be some other configurations that you can realize the spherical motion, but in this case, it is clearly not a spherical workspace. It's something different, right? It's not a spherical workspace in this specific example, right? So yeah, I hope we can move on to the next question. So the correct answer, if you check, it is indeed option D. So moving on to the second question. So the NSA are the normal, sliding, and approach vectors of the transformation matrix. Which of the following sentences is not true? Right? So as I've already said, this N vector, NSA are vectors, NX, NY, NZ, SX, SY, SZ, AX, AY, and AZ. And this rotation matrix R is an orthonormal matrix. So which of the following sentence is not true? So we'll
N
consider
dot N cross N equal to 0. That may be wrong. And
cross and okay, this could be wrong. Anything else? What is N cross S?
N dot A also 0. That is also wrong.
N dot A is wrong. Is it because
Cos 90, na?
yeah,
Cross product means cos 90.
okay. Yeah, so N and A are orthogonal vectors, so that is also false. Yes. What else?
Only those two, sir.
So N
I
cross
think
S
that
is A.
all are orthogonal. So N cross S will give the A.
Ah.
Maybe the minus, we are not considering the polarity. If we are not considering the polarity,
We
N
have to
cross A
consider the
also A.
minus. So N cross A is minus S, right? So this is not true, I think. This is also
Okay.
false.
So we have considered the sign also, sir.
Yes. That is also false. And S cross A is N. That is true. And S dot S is 1. That is also true. So I think there are two wrong answers. These two are wrong, I think. Do you agree with that? Or sorry, we have three wrong answers, I think. This, and this. Right? Okay, so we'll check the answer, I think. Oh, it says only this answer is correct. Maybe the answer key is different. Which of the following sentence is not true? N cross N is obviously not true because their angle is 0 degrees. Angle between the vector and itself is 0 degrees. So cross product of a vector with itself is 0. Uh, and N dot A is also 0 because yeah. Yeah, so I think the answer key could be wrong, but these three are obviously wrong, right? I think those are obviously wrong. Those should be wrong. So yeah, maybe we'll have a check with this, but I believe option uh, B is wrong and options C, sorry, D and E are also wrong. So these should be the correct answers. It's a multiple correct answer question. So these are all wrong. Yeah. Okay, so moving on to question 3. For a spatial serial manipulator, the forward kinematic relations are given as follows. So this is the x coordinate, this is the y coordinate, this is the z coordinate. So what is the value of theta 3? Sorry, what's the value of cos theta 3 if theta 1 is 0? So if you can directly substitute theta 1 as 0 to this equation, so x would be, so if theta 1 is 0, cos theta 1 would be 1. So this will be a2 cos theta 2 plus a3 cos theta 2 plus theta 3. And y would be 0 because theta 1 is 0. This entire term will get cancelled. And z would be d1 plus a2 sine theta 2 plus a3 sine theta 2 plus theta 3. So this is a problem of inverse kinematics. You are given a forward kinematics relation that maps between theta 1, theta 2, and theta 3 to x, y, and z. So for a given x, y, and z, what should be, how would you derive, or what are the values for theta 1, theta 2, and theta 3? So this question specifically asks for cos theta 3. So how would you do this? So the easiest thing is to do this. There are similar terms. A2 cos theta 2 over here, A2 sin theta 2 over here, A2 cos theta 2 plus theta 3 is here, A3 sin theta 2 plus theta 3 is here. So if you encounter with these sort of equations, more or less identical equations, but sine and cos are interchanged, it's always better to square and add these terms. You will get some additional clue. So if I write this as equation 1, and if I write this as equation 2, and if I rearrange this, if I, on the left hand side, if I do this x square plus z minus d1, the whole square, if I square and add these two equations, what will you get? So the right hand side of the first
A2
equation would,
square plus A3 square, sir.
are you sure? Because if I expand this, a2 square cos square theta 2 plus a3 square cos square theta 2 plus theta 3 Then we have one more term, 2a2 a3 cos theta 2 cos theta 2 plus theta 3. Then we have a2 sine a2 square sine square theta 2 plus a3 square sine square theta 2 plus theta 3 plus 2a2 a3 sine theta 2 sine theta 2 plus theta 3. So now how would you simplify this? These two terms, a2 square cos square theta 2 and a2 square sine square theta 2, that will become a2 square, right? This becomes a2 square. And these two terms, a3 square cos square theta 2 plus theta 3 and a3 square sine square theta 2 plus theta 3, that will become a3 square. Then we have these two terms remaining. That will be 2a2 a3 multiplied by cos theta 2 plus theta 3 plus sine theta 2 sine theta 2 plus theta 3. Right? So how would you simplify this expression? Now you can use the trigonometric identity uh, cos A minus
Theta 2
B.
plus theta 3 is like A, and in place of B, theta 2, it is of cos of A minus B.
Yeah, cos
Then
of A
theta
minus
2
B.
plus theta 3 minus theta 2.
Yes, correct. Theta 2 plus theta 3 minus theta, right? Cos A cos B plus sin A sin B. So if I consider if I consider A as theta 2 plus theta 3 and B as theta 2, so this entire term will become cos theta 3, right? I hope I'm correct.
Yes, sir.
Okay, so now our left hand side is x square plus z minus d1 the whole square. This will become a2 square plus a3 square plus 2a2 a3 cos theta 3. So our cos theta 3 would be x square plus z minus d1 the whole square minus a2 square minus a3 square by 2a2 a3. I guess this will be our answer in case of this question. And I think the correct choice is option
B, sir.
B. Option B. Okay, yeah. Yeah, so that is indeed our answer. Moving on to question 4, it's a true or false question. It says the forward kinematics is the transformation of kinematic information from the joint variable to the Cartesian coordinate space of the final frame. So as per the DH approach, the forward kinematics is basically transformation matrix addition. Is it true or false?
False, sir. We are multiplying the transformation.
Transformation matrix, right? Yeah, exactly. Because we have, if you want to map from 0 to the nth frame or the end effector frame, we progressively multiply the successive transformation matrix n minus 1 to n. So that is indeed false. Okay, it's matrix multiplication. So question 5, the forward kinematic model of a planar polar manipulator is given as so and so. So I'll rewrite it over here. X is d cos theta. What is this? D cos theta, and y is d sine theta. So this planar polar manipulator, you can also call this as an RP manipulator. Right? We have seen this example earlier. where d and theta are the joint variables. So the inverse kinematic solution of the system, when the desired x and y are respectively given as 30 mm and 45 mm. So if x is 30 mm and y is 45 mm, what are the solutions of
D is equal to root of x square plus y square.
x square plus y square? Yes, theta will be. So if you divide these two equations, 2 by 1, if this
Y
is
by
equation
tan
2,
inverse y by x.
yes, this will be tan inverse y by x. And I'm not sure about the numerical values. I think this should be approximately 54, and this should be approximately 56 degrees, I think. But it's fairly straightforward to solve this numerical problem. Okay. Yeah, I think the answer is 54 and 56. For D and for theta, it's 56 degrees. Okay, so for the sixth question, we are asked to find the DH parameter for the second joint. So you can consider this to be a revolute joints, no problem. Even if you don't consider that, it's not going to be an issue. So for the second joint, we need to find a mapping between the first joint to the second joint. Right? How do we do that? So I'll simply draw the first and second joints only. So if I label this as x1, sorry, I'll use the respective colors. If I use this as x1 and z1 is perpendicular to the plane, z1, and yeah, what else do we have? We have z2 to be like this. Z2 is green colored, I think. Yes, this is Z2, and X2 would be like this. So what should be the DH parameters? Yeah, the joint parameters are actually given in the question. So the first joint parameter is theta1 and the second joint parameter is D2. So this robot will rotate about this axis. The first joint will rotate about this axis and the second link will translate about this axis. So if that is the case, what is the DH parameter for the transformation 1T2? So you have to find out alpha I minus 1. That is nothing but alpha 1. So AI minus 1, that will be A1. Then theta I, that will be theta 2. Then DI, that will be D2. What would be the case? So, yeah, alpha would be the rotation about x1 axis, right? How much should we rotate about x1 axis so that z1 and z2 would be aligned or parallel? So right now z1 is out of plane and z2 is horizontal, parallel to the plane.
Pi by 2, sir.
So that is pi by 2. And
A1
A1
is
would be, yeah,
D2. Is it
A1 is actually the displacement along x1.
along x, sir?
Along x1, yeah. These two are with respect to x1 axis.
Then 0, sir. Okay, then 0.
These two are with respect to z2 axis. So now A1 is 0 because you don't have to move about x1, right? Okay, now x1 is now here. Z1 we have already aligned it like this. Now what is theta I? So x1 theta I would be how much do you have to rotate about z2 so that x1 and x2 will become aligned.
It is 0, sir.
That is 0 because it's a
Already,
prismatic joint and there is no
uh,
relative rotation between x2 and x1. And d2 would be the translation or the distance z2, distance along z2, so that these 2 points will coincide, or the perpendicular distance between z1 and z2 can be compensated. So this was, in this question, it is given as, this distance is given as d2. So you have to move d2 along z2 so that these 2 points, the offset between these 2 points can be taken into account. That itself is, d2 is nothing but d2 itself. So I hope that is clear enough. I think the answer is
yes,
option
sir. B, sir. I
B.
think.
Yeah,
B.
pi by 2. Yeah. Okay. Okay, similar question. For the given diagram, find the DH parameters for the second joint. It is an active rotary joint. So yeah, DS parameters for the second joint. So this is the first joint. This is the second joint. We need to find out the mapping between the first joint and the second joint. 1, 3, 2. So we have alpha I minus 1 as alpha 1, AI minus 1 as A1, theta I would be theta 1, VI would be D1. Yeah, I'll redraw the corresponding axes. So this is Z1, this is X1, and if this is Z2, this is X2. And in the question, the link lengths are not given actually. These length and this length, none of the lengths are given. So yeah, we can see it like A1's here. So maybe we can consider this distance to be A1. Does not matter. We can consider that to be A1. It should be A1 or it should be 0, no problems. So what is alpha 1? So these two are rotations and translation with respect to x1 axis, and these two are rotations and translations with respect to z2 axis. So the first parameter alpha 1 would be how much do you have to rotate with respect to z1, sorry, x1, so that z1 and z2 would be aligned. So z2 is out of plane, z1 is parallel to plane, and that too
So
along vertical.
pi, sir.
It's pi by 2, right? Because if you rotate z1 by pi by 2, it'll be like this, right? If you rotate it by pi radians, it'll be vertically downwards, right? It,
So
it
it
may
is pi
be,
by 2, sir. Now it is pi by 2.
yeah, pi by 2. It may be a bit difficult to visualize because if I represent this as out of plane vectors, it could be difficult to visualize. Yeah. And A1 would be how much do you have to move along x1 so that the perpendicular distance between z1 and z2 will be taken care of. So A1 would be distance by distance you have to move along x1. So the question, if you consider this as the link length, A1 as the link length of link 1, you have to move A1 units along x1, right? So the perpendicular distance between z1 and z2 is taken care of. And what about theta 1? So theta 1 would be the rotations that you, the amount of rotation that you have to rotate about Z2 so that Z1 and Z2 will be aligned.
X1 and X2, sir.
Sorry, X1 and X2,
Correct.
yes. How much would that be?
0, sir.
It will not be 0 in this case because it says it says it's an active rotary joint. So the position of x2 will be given by this rotary joint variable theta2. So it
Theta
need
2,
not
sir.
be, yeah, it need not be in
Yeah.
this orientation. It can be like this, it can be like this, it can be like
Okay,
this.
sir. Okay, sir.
Yeah, so that is theta2. And di would be the distance you have to move along z2, right? So that the perpendicular distance between x1 and x2 can be accommodated. So like since they are already, the perpendicular distance between z1 and z2 are already 0, you don't have to move any units along z2. So in that case, d1 is 0. So our ds parameters is pi by 2 a1 theta 2 0. I think that is also B, option B. Check the answer. That is indeed correct. So we have 5 more questions. I'll try to quickly wrap this up. So it's a true or false question. For the inverse kinematics problem, the numerical method can be applied to all kinds of serial manipulator robots. So that is true, just like what we have seen in the theory, because analytical approach may not be available as the robot's complexity increases, but you can use this numerical method for any all kinds of robotic manipulators. So that is indeed true. Moving on to question 9. So out of the 4 DH parameters, which of them are link parameters? So it's more or less the definition of this DH parameters. There is no other way apart from to really learn about these definitions, possibly by heart if that is that works. But basically, link parameters conveys the relationship between joints, and joint parameters basically conveys the relations with respect to links. So which of the question asks which of them are link parameters, right? Like we have we have 4 DS parameters: alpha I minus 1, ai minus 1, theta I, and ei. So the name of this thing is called link twist. And as per the definition, link twist is the angle between zi minus 1 and zi measured above xi minus 1. And the second parameter is called link length, right? So link length is nothing but the distance between zi minus 1 and zi measured along xi minus 1. And the other two are nothing but joint angle and joint distance, right? And these two parameters conveys the relative position and orientation of the joints. And these two conveys the relative position and orientation between two links. So the question specifically asks link parameters, right? Link, and obviously these two are link parameters because one way to remember is they have links in their names. It's called link twist and link length. So link length is obviously a link parameter, and so is link twist. Because link length cannot be a joint parameter because link length basically defines the length of the link. And the length of the link is nothing but the distance between adjacent joints. So I hope I'm not confusing, but yeah, the link parameters are link twist and link lengths. So these first two options are indeed the correct choice, A and B. Okay, so moving on to question 10. I hope the font size is all right. I'll simply enlarge this. So the following figure depicts a skeletal diagram of a R perpendicular to R parallel R robotic manipulator. The frames and the joint angles have been marked for you. Okay, so again, we may have a short break in 10 minutes. I tried to wind it up by 10 minutes. Otherwise, please join back. So consider the link lengths between frame 0 and frame 1 to be L1 and between 2 and 3 to be L2. So This should be L1. This should be between frame 2 and 3. It will be L2. Find out the correct DH parameter table for the given case. Right? You have to find out the DH parameters for this given case. So I'll label the individual parameters alpha I minus 1, then AI minus 1, theta I, and BI, right? So yeah, for the first link, we'll consider the transformation between frames 0 and frame 1 over here, right? I hope maybe if I want, I can redraw the frames. So Z0 is like this. X0 is like this, right? And Z1, as per the diagram, Z1 is vertical like this, and X1 is like this. Sorry, right? And Z1 is actually a rotary joint that will have a joint parameter theta1 like this, right? So what would be the relationship between 0 and 1? And the length between 0th frame and the first frame is L1. So what is alpha I? Alpha I would be alpha 0. That would be the rotation that you have to make about X0 so that Z0 and Z1 would be aligned. So as you can see, since they are already aligned, you don't have to rotate by any amount. So alpha I minus 1 would be 0.
0.
Yeah, AI would be the distance you have to move along X0.
L1.
No, you don't have to move along X0, right? You have to move along Z0, L1,
Okay.
right? X0 is along this direction. I hope that is clear.
AI minus 1 is now 0, sir.
AI is the distance you have to move along X0.
Along X0. Okay.
X0, yeah. And now they are already aligned. You know, they have frame 1 and frame 0 have equal X coordinates. So you don't have to move along X0, right? If you move along
Okay, sir.
X0, they becomes it'll become somewhere here. You know, you have to make sure that this frame reaches this frame. But you don't have to move along X0. You only have to move along Z0,
Okay, sir.
right?
So
So the
AI
first
minus 1 is 0. Yeah.
AI minus 1 is 0, yes. And theta I, what would be theta I? Theta I is nothing but the angle you have to rotate about Z1 so that X1 and X0 will be aligned. And note that theta 1 is a revolute joint, X1 can be anywhere. You know, it need not be like this. It can be anywhere, you know, along that plane.
Where is the statement, sir? Where is the statement?
What statement?
R theta.
Yeah, it's a revolute joint, right? In the question, it says it's a revolute joint. And in the diagram, it says it can rotate theta 1. This joint, Z1, can rotate by an angle
Okay, sir.
theta 1 about the vertical axis, right? So to align X1 and X0, if X1 is rotated by an arbitrary theta 1, you have to rotate X0 by that same amount about Z1 so that both of them will be aligned. Right? So theta I would be theta 1. And what about DI? DI would be the distance along Z1. Distance you have to move this frame along Z1 so that the perpendicular distance between X1 and X0 can be taken into account.
Then it is L, sir.
That is, yes, L1. Correct.
Yeah.
Yes. Now, what would be the transformation between frames 1 and frame 2? So Z2, I'll draw it like this. So now this is, sorry, now this is Z2, and X1 and X2 are along the same uh, axis. X2 is also along the same axis. So now what is the how do you transform Z1 frame 1 to frame 2? So the first variable would be alpha I minus 1. Again, it is the rotation that you have to make along x1 so that Z1 and Z2 will be coincident, or it'll align. Rotation you have to make about x1 axis so that Z1 and Z2 would be aligned.
Either it is 3 pi by 2 or minus pi by 2.
Pi by 2, that is correct. So I'll write it as minus pi by 2 or 3 pi by 2. And what would be AI? The distance that you have to move along x1 so that the perpendicular distance between x1 and x2 would be taken into account. As you can see, they are already intersecting. Z1 and Z2 are already intersecting. There is no perpendicular distance between Z1 and Z2 that you have to that you can accommodate if you move along x1. So that is 0. And what is theta I? Theta I now would become the angle that you have to rotate about Z2 so that x1 and x2 will be aligned. See, so based on this joint variable theta 2, x2 can be like this. So x2 will be along this vertical plane, you know. One instance it can be like this, another instance it can be like this, it can be like this, like this, like this. It will be parallel to this plane of this board. So at this moment it is aligned x1 and x2. That does not mean that it will be always like that. So the position of x2 would be characterized by this joint variable theta 2, right? So the angle by which you have to rotate along Z2 to compensate the angle between x1 and x2 would be theta 2, right? And the final transformation would be the translation along Z2 so that the perpendicular distance between x1 and x2 can be accommodated. Again, since both of these frames are already intersecting from the start, there is no perpendicular distance between x1 and x2. So di will also be 0. Hope that is clear. Okay, so one more final transformation between frames 2 and frames 3. So I'll try to make this a bit small. Yes. Yeah, and as per the diagram, Z3 would be something like this. This would be Z3 parallel to Z2. X3 is also parallel to, yeah, this is X3. Now, what is the joint parameter? Like Z3 can also rotate by an amount theta 3. Session. Yeah, now the transformation is now between theta frames 2 and frame 3. So how would it look like? So yeah, the first is alpha I minus 1. That is the rotation that you have to make about x2. So this is x2. right? Rotation you have to make along x2 so that z2 and z3 will be aligned, right? So as you can see, they are already aligned. Z2 and z3 are already parallel because
Yes,
there
sir.
are two
That is
parallel
correct.
joints. Sorry?
They are parallel, so the zero, sir. Alpha.
It's zero, yes. And second is AI, the distance that you have to move along x2 so that the perpendicular distance between z2 and z3 can be taken into account.
That is L2, sir.
That is L2, yes. And theta I would be the degrees by which you have to rotate about z3 so that the orientation between z2 and x3 can be taken into account. So since x3 is a revolute joint, it can be here, it can be anywhere at any instance actually, about a vertical circle, right? So that relative orientation between z2 and z3 will be given by this joint variable theta 3. So that will becomes theta 3 and di would be the distance by which you have to translate along z3 so that the perpendicular distance between x2 and x3 can be taken into account. And already from the beginning itself, x2 and x3 lie along a same line or they are collinear. So there is no perpendicular distance between x2 and x3 that you need to accommodate along z3. So that makes this zero as well. So this is our DH table. And I think the correct option in this case would be, there are 6 such options. I think which option has minus pi by 2? All of the options has pi by 2. Yeah, I think option A is the correct choice, if that is the case. Okay, checking the answer. Yeah, option A is indeed the correct answer. Moving on to the second last question. So for the given diagram, find the DH parameter for the second joint. So the second joint is an active rotary joint. So this is the second joint in the figure. Second. Yeah, this is the second joint, Z2. It's a rotary joint. So we need to find the DH parameters between frames 1 and frame 2. So I'll draw the frame. Z1 is like this. X1 is like this. And Z2 is vertically upward. And X2 is like this. And this is an active joint variable, so it can rotate about this vertical axis by theta 2. Okay, so, and the offset between perpendicular distance between x2 and x1 is given as d2 in the question. So what is alpha I minus 1, ai minus 1, theta I, di in this case? So I is 2. So alpha I minus 1 would be the rotation that you have to make along x1 so that z1 and z2 would be yeah, z1 and z2 would be aligned.
3 pi by 2, sir.
That is 3 pi by 2. And ai minus 1 would be the distance that you have to move along x1 so that the perpendicular distance between z2 and z1 can be taken into account. So the perpendicular distance, if you extrapolate this, z2 and z1 basically intersects, right? The line of action of z2 and z1 intersects. So there is no perpendicular distance between them that you can accommodate along x1. So ai minus 1 is 0. right? And theta I would be the relative orientation between x1 and x2 about the vertical z2 axis, this one, right? So that will be theta 2. And di would be the perpendicular distance between x2 and x1 along z2. So this is x2, this is x1. The perpendicular distance is d2. Measured along z2 is this, like d2 itself, d2. So in that case, the correct answer is, I think, option B, right? Yes, that is indeed correct. Okay, moving on to the final question. Which of the statements are true? So yeah, using numerical methods for solving inverse kinematics will yield all possible solutions. Is this true or false regarding numerical methods? So this is not true because numerical methods usually cover to a single solution, depending on the initial condition that you would be, initial guess that you would be giving onto the solver, right? Unlike analytical methods where you can solve for multiple solutions, numerical methods will only converge to a single solution that also depends on your initial condition. Question 2, accuracy of the numerical solutions are dictated by the user. So that is true because you can determine the tolerances between two successive iterations as a termination criteria. Option 3, analytical methods take a fixed number of operations to solve inverse kinematics. That is true because you already know the equations. It's easy to estimate the number of operations, arithmetic operations such as addition, multiplication, division, all those sort of things. The fourth question is numerical methods can be applied to all robots and is most desirable for real-time control. So the first part is actually correct. It can be applied to all robot, but it's not really desirable for real-time control because you don't know the computational cost for it because everything happens behind a black box. So it may take a long time for it to converge to a solution. So in that regard, it's not, it cannot be ideal for real-time control. So yeah, I think option this is also false, and it's most desirable for real-time control. So the question says which of the statements are true. I think the true statements are options B and C. Right? If you check the answer, it is indeed options B and C. Right? I hope we don't have any conflict in these questions. Yeah. So we have reached the end of today's session. So
Sir,
yeah,
sir, in assignment 1,
yeah.
whatever fill in the blank is there, we have kept right hand. That means in your solution, you might have given only right. And then as we have written right hand, we got 0 marks, sir. Can we expect
Assignment 1, right?
Yes, sir. I think the fill in the blank, sir. First I
Do you
kept right, but
do you
hand
recall the
is
question?
there in the sentence, but
Yeah.
still we have kept the right hand.
Do you recall the question for assignment 1? Which question was that? Uh,
Sir, whom we will address, sir?
Sorry, I don't have that question with me right now. So I would ask you one thing. If you have access to the discussion forum, if
Okay,
you
sir.
if you can log on to that Google discussion forum, you can actually raise this issue. If you feel that the you have written a right answer, but still you got incorrect as or 0 marks, you can raise it, and we will raise it to this NPTEL team if it is unfair,
Okay, sir,
right?
but again, for every assignment, more than 10 questions are existing, sir.
Yeah.
It is lengthy one. Listening the videos itself, and we are in a hurry.
Yeah.
Actually, in this assignment also, the things are repeated. Already we have done the exercise for
Yeah.
the DH parameters, even in the
Uh,
assignment 1, 2, and still here we got the same question. And not same, means same model.
yeah. Because 2 and 3 are more or less the same topics, right? Because in week 2, it was only a brief introduction to DH parameters, and in week 3 we actually solve a few inverse kinematics problems, but they are more or less overlapping. So that is why we have this, you know, repeated questions and all those things. And maybe from next week, week 4, we'll go on to this, velocity analysis, and week 5 we'll go with dynamic modeling. So like we'll have lesser and lesser overlapping topics, right? But I think what you meant is you may have you think that your solution is right, but you got wrong answers for it, right? For assignment 1, is that the case?
Yes, sir. I will write in the discussion forum, sir.
Okay, okay. If in that case, please let us know that specific question in the discussion forum. We'll forward it to this NPTEL team, right, for a revaluation. Okay. Okay. So if there are no, if there is no other
1 minute, sir.
questions.
Just I am verifying.
Okay.
Assignment 2, sir. Second question. Assignment 2, second
Okay.
question, sir.
Assignment 2, second question.
Mm.
Okay, we'll review this.
And again, in the third question also, in the discussion, we thought that in a prismatic joint, what are the constant kinematic parameters? We
Yes.
thought that the 3 parameters are constant, but here the answer is only 1 parameter. That is the link twist is the right answer. But we
Yeah,
kept link twist.
for prismatic joint, the constant parameters are link twist, link length is also constant,
That
joint angle
we
is
discussed,
constant.
sir. I kept the same
Yes.
thing, but answer is link twist, the last one, sir. Third question.
That is not correct. That is not correct.
That
Joint, the only variable is that joint distance. Everything else should be constant.
and another one is maybe my mistake, sir. The location at which a coordinate frame is attached to a rigid body in a multi-body system as per non-standard DH parameter convention. I actually seen the center of gravity and I have kept the center of gravity, maybe the wrong answer.
Oh, that
And
is the
our
wrong
right
answer.
answer is the
It's at the
proximal joint.
proximal.
Proximal.
Yeah, that's
What
correct.
is
That's
that?
correct. It's at the
Okay.
proximal end.
So please
Yes.
consider second question and third question, sir.
Okay, okay.
Second one.
Third question.
Assignment 2, sir. Assignment 2.
Yeah, segment 2. I've noted it
Okay.
down.
Thank you, sir.
Okay, thank you. I'll look into this Okay.
Okay.
Okay. So thank you for joining
Thank
in.
you, sir.
We'll see you next week. Thank you. Okay.